ability to print conducting materials and dielectrics. Basically, when we say print, we don't 3D print an object. It's more like a 2.5D printing, right? So it's we print metal patterns. So we have few patents that are granted several primarily funded by NASA, different phases. And we have been selling equipment so far to universities and federal labs. So before getting into the actual flight demo data, like I just wanted to give a very brief overview on why this materials processing in microgravity is important. By the way, please feel free to stop me at any time, ask any questions. So, obviously in Earth, gravity dictates manufacturing. It works to our advantage. What is missing is that, like, can we make use of absence of gravity to our advantage, and can we use space or moon as offshore manufacturing? Details around this, how the materials would behave in microgravity, how the crystal structure formation is, microstructure formation is going to be, how the both mechanical and electrical behavior or optical properties will behave when they are processed in microgravity. So there's like whole lot of information gap that is there. And that is why understanding this microgravity research is actually extremely important. And then, obviously we are limited with finite resources here in Earth, which is, primarily controlled by geopolitics. And there is a lot of push now by many countries to look for resources up in moon and also in asteroids. So obviously NASA's first, this lunar mission for this decade is going to happen by 2024. It won't be like the previous Apollo mission. So they're going to send people and have continued presence. It's going to be like International Space Station, not one-off visit, right? And in order to have a continued presence in moon, they really need to have infrastructure built. So they, building the infrastructure, unlike the previous mission, Apollo mission, this mission is going to be primarily first infrastructure building in moon before sending humans to space. So that's going to be one of the major focuses, and later on, use that for any Mars or forward capabilities. This is one of the old NASA roadmap slides where, the International Space Station was basically set to retire by 2024. So basically move on from International Space Station to lunar in 2020 is the plan, and then in 30s look for Mars. But fortunately, the ISS got its extension up to 2030. So only in 2030 it's gonna retire. Until then, we have the facility to do as much research as possible to better understand these materials behavior in microgravity. So one of the focus for NASA has been on-demand manufacturing of electronics. Looking at a range of things. Solar panel is one of the major focuses. I started off working with biosensors fabrication. That's my background on, like, I did my PhD and postdoc in Ireland, working on biomedical applications for plasma processing. So we were initially looking at that because the astronauts will have, the biosensors have limited shelf life. So it's better to manufacture sensors on demand. And there are multiple applications like energy storage and antenna, all these things. See, what has happened is that over the past few years, there has been drastic changes in the space policy in US. If any of you can notice the apparent difference, there are applications that a lot of people are working on space-based solar power generation, convert that into RF and then beam it back to Earth. So it's a heavily funded project that's going on. So that's one of the cleanest form of energy that you can have. Just generate, get the solar panels deployed, really large structures, manufacture and deploy in space, get the electricity from there, beam it, using RF. The second part is, NASA's interest, which is on-orbit assembly and manufacturing, and ISS has been a major driver for this. What is very interesting is that if you see DARPA Nomad, is a project that was launched 2 years ago called Novel Orbital and Moon Manufacturing by Defense. So generally, historically, space has been like NASA has been the only organization looking into space, anything beyond low Earth orbit, right? Of course, defense was using, trying to look at space for like their energized weapons type of thing, but nothing more than that. But this is a drastic change in the policy to help NASA or pursue, work in parallel to have lunar manufacturing. So this is definitely going to happen. There are multiple countries that are actually racing now, and obviously multiple companies that are also eyeing on the, obviously resources, you can say. So different application that kind of comes to my mind about, high temperature electronics, phased array antenna, metallization, alloy manufacturing. These are, some of the important parts that is being looked at. And another very interesting thing that happened again over the last 2 to 3 years is building up of these private space stations. The primary driver for this is, because Elon Musk brought the launching cost extremely down. Just to give an example, it was used to be like $50,000 per kilogram of payload to send to ISS. He brought it down to less than $3,000. He is looking at now bringing it close to $100. So then it's going to be just that will happen, and that actually kind of it enabled all these private companies to look for on-orbit manufacturing. And then the bottom one that you see on the blue origin is like they have a space research park. Jeff Bezos is looking into the space research park there. And some of the applications that have been extremely important, that could really impact human lives here on Earth, is manufacturing of these components like fiber optics, alloys, super alloys, pharmaceutical components, and there's also effort. Vardha Space is looking into semiconductor manufacturing. Human organs is one of the most important things that's going on, because when you're printing in microgravity, you don't need support structure. So basically, you can print organs, without having to worry about having a need for support structures. One of the main challenges there is when you bring it down to Earth, it would collapse, right? So Axiom Space is looking into that. Vardha Space is looking into that. They are trying to solve the re-entry problems. So now all these private players are getting in there, and then mining is also getting more attention. One of the things here is, Earth has a magnetic field. So, we are protected by any solar flare event, but Moon doesn't have a magnetic field there. So what has happened is that over the past millennia, all the solar flare, gets bombarded onto the Moon lunar surface, and helium-3, which is very rare in Earth, is actually available in plenty in a lunar surface. So, and you can use helium-3 for fusion, and that's gonna, you know, unlike uranium, the nuclear fission, fusion doesn't have radioactive decay. The byproduct here is proton. So it's going to be one of the cleanest forms of energy that we can think of. And there's already a private company that has raised over 2 billions to develop nuclear fusion reactor for commercial use. And then, they don't obviously use lunar helium, but, you see where it is going, right? So, and then the mining, all these things are going on. And eventually, a lot of these dirty jobs could be like that, spoils the earth, could be transferred over to moon, so that we can help keep the planet clean. That's one of the goals as well. So where does Space Foundry fits in this, and how are we gonna enable, contribute for the space economy? Is that, we are looking into commercialization of low Earth orbit. That means like manufacturing in International Space Station. Some of the applications that we have already identified is in phased array antenna, um, um, and metallization and interconnects for solar panel manufacturing and alloying and metamaterials. See, the solar panel manufacturing in space is actually being pursued by multiple organizations. DoD is very actively funding because they want, so they're looking at deploying solar panels that are in the range of 2 to 3 kilometers in length. It's no way, we can take everything from Earth. So they're really looking at manufacturing in orbit and deploying it there. So we feel like, we are going to be a key contributor to enable some of the applications like metallization and interconnects. And then we are in discussion with lunar manufacturing, because in 3 years, they want to have some feasibility. So it's the zero gravity demonstration has really opened up a lot of opportunities for Space Foundry. And we are also looking at printing of antenna on CubeSats and solar sails. That's basically manufacturing in Earth for space. So coming to the core problem that we are solving here, printed electronics industry has its own problems. So one of them is that there's a heavy reliance on ink quality. The ink metal inks, they tend to oxidize or they aggregate. The processing is challenging in the sense it needs multiple process steps. If you are printing, a thick layer using an inkjet or an aerosol jet technique, you have to print and cure. Building thickness becomes very challenging because the atmosphere is going to just oxidize. Say, for example, copper. Getting a say 200 or 300 micron thick copper is going to be extremely challenging. You're going to have intermediate copper oxides. And environmental issues is another issue. So Space Foundry is focusing on plasma jet printing. So basically, we're using atmospheric pressure plasma. It's like a pen, you can say, to dry print metal oxides, dielectrics in a dry format. So there is no curing involved. And then, just like, when you do PECVD, for example, you use a gas silox, and you can use tetraethyl orthosilicate or hexamethyl disiloxane. All these hydrocarbon, silicon oxide based hydrocarbons, you don't really worry about the quality of that gas content. You work on the plasma to reduce all the hydrocarbons and get high quality silicon oxide, just for an example. And same with diamond growth, right, when you use methane. So a similar concept here instead of, all the companies that are focusing on printed electronics, they are working on, um, getting high quality inks, right? They don't have plasma component in it. They use plasma for pre-treatment, not for printing. So what we have done is the ink actually goes through the printhead, and plasma reacts to it. So we kind of um, reduce the dependency on ink supply chain, and the inks can have, just like how you store your gas cylinder for ages, you're not going to have much issues. The same way the inks that we use for plasma have no shelf life issue, no nanoparticles and liquid waste. Of course, we use a liquid precursor, but it's like a very simple solution. We can also use off-the-shelf inks as well. We're kind of ink independence is there. So you've printed a wide range of materials so far, but our company, is primarily focusing on copper and silver as of now. Some basic like copper prints on a range of substrate using our proprietary ink. We are somewhere around about 60 times the bulk resistivity. So we are working towards getting it lower than 10x. In the next few months, we will have it done. Some of the antenna prints like X-band and Wi-Fi antenna that we have been printing on a range of substrates. We are in discussion with some corporates to commercialize this. This is for a defense customer. We printed an X-band antenna on it's on a ceramic alumina. This is the conductivity. So what is interesting is that we can also print pillars. We can print, continue to have the print head position so that you slightly build a three-dimensional structure. Okay, so now getting into the microgravity flight demo. So our goal was to show that, like, plasma in principle works in microgravity, but we are not sure the entire hardware that we have built is going to interfere with flight hardware and cause any issues. So we needed to check that. And then fluid delivery is a major issue. Handling fluid is one of the most difficult aspects in microgravity. So we needed to check that, and then we needed to print copper and silver. And so the NASA really wanted us to do risk mitigation, and they said, like, use at least one off-the-shelf ink so that that it works. And then you can use your own proprietary ink to show that you can do better. So needed to print lines, pad, electrodes, and antenna. So one of the most difficult things, not difficult, it's very time consuming that you will have to do when you do a flight demo, is this providing this payload integration package, where you provide a complete design of the package. I think 3 months ahead of the flight, 3 or 4 months. And you have to have a lot of things nailed down. It's not difficult, it's just time consuming. You need to have a complete plan on how you're going to vent, and electronics interference. So we were there, and then the very first day where there will be a technology readiness review before loading onto the aircraft. People came for review. The entire panel was there because we need to show how it works. They're gonna interfere, ask questions, and then see how it works, and then only they allow it to load to the aircraft. The moment we plugged into the outlet, there is this GFI interface that kept the circuit kept breaking. So we had some electrical issues, ground related issues between our AC and DC. Some of the equipments, some of the parts are using AC, some using DC. It was like, there was some issue, and then we could not fly that day because we could not fix the issue. See, one of the most important things is that when you identify a issue, you're really racing against time. You got to fix that within, say a few hours, basically. So the first, and then we fixed it, and then overnight we actually worked 36 hours non-stop. The entire team was there. We did not leave the facility. And then we made it work, and then we loaded it on the aircraft, and then we were up in the flight. There was a wiring problem that we really underestimated. So, we did not expect that to happen. And, basically we lost communication. The whole flight, we were so stressed, the communication, one of the soldering joints kind of got disconnected, because the flight, when it flies, it goes from 1G to 2G, and then from 2G it drops to 0G, and then it goes again 1G to 2G. So when it goes in this cycle in 2G, basically you get pulled, right? And then there is a release. So all these solderings and these wirings are we need to pay closer attention to all these aspects. So it was a mess. We really did not know about all these things. So such heavy cables lying on thin cables. What happens in the 1G to 2G to 0G transition is that if there are thin cables, if there are heavy cables sitting on top of the thin cables, the pull that the heavy cable will experience on 2G, it's going to be much more, it will be pushing the thin one. So there's like, you gotta, when you design the experiment, the hardware, you got to really take all of this into account. And then we kind of, went to Kennedy Space Center in Florida. They kind of opened up the box, electronic control units, and said that, how do we really fix some of these things? You can also do rigorous shake testing, but that is not needed, because when you are doing a rocket launch, maybe you will need to do a shake test, but this is general flight. So they said, okay, you don't need to do a shake test, but at least make sure that all the cablings and all these wirings are done in an appropriate manner. And then we had to shake it, see whether if anything disconnects. So we did some risk mitigation thing. As I mentioned, the communication failed. The router, the cable that we had to the GUI was, it got disconnected. We did not know in that thing. So all the failure points were identified, and we tried to fix that. These sagging electrical wires are a major concern, right? It needs to be fully secured. You got to tie them, right? And then on the second flight, also in the first flight, we realized that manual intervention is not going to be happening, because we have very less time. We get about 20 seconds of microgravity, basically. And then within that, you have to go for 1G, 2G, you have to lie down because you get a pull. Unless you have gone through a few flights, how you can, at least control yourself. You got to just lie down for the first two flights, when this transition happens between 1G to 2G. So, you have to lie down, get up, and then immediately lie down after 20 seconds to protect yourself. So it's very difficult. So what we decided to do is have an accelerometer connected in the printer, and then everything was programmed. So we have proper all this G code, M code were integrated. Every hardware is PLC controlled. So we had to do all this coding thing within one day. Like, we had accelerometer earlier. We thought, okay, it's fun to have, but fortunately, we had brought it with us and integrated. And then overnight, we had to do all this coding to get a completely, setup for complete remote processing. That means like without intervention, we needed to be printing. And then, the printhead, what it would happen is that the printhead would move uh, to a parking position or a dump site. And then as it sees triggering, the accelerometer sees the G varies, goes to 1.6 G or higher, then it goes to a printing position. And then immediately within few seconds, you will get 0G, the print starts, right? And then it will go to the another parking position. So it kind of, we programmed it very well. The second day, we thought it's going to work, and then it still did not work. So there was some issue in some of these cabling. So we in ground, we take it for granted. Basically, tubings, we mix and match. Tubes that are meant to work for liquid, we use for gas. That are meant to use for gas, we use for liquid. As long as it works, we just deal with it. But what happened is that we had used one of the mass spectrometric the things that we use for HPLC tubing. We had used it for liquid, and we had actually over tightened it. So there was just a little gap for the ink to flow, and there was a pressure buildup. So the flight, it did not work. So the second flight also did not work. And then we identified, the problems and tried fixing it and demonstrated in ground. Okay, now it's working. Now, get a set point. And then in flight 3, we fixed all this. It worked. But there were like droplet formations, right? Like as you see here on the picture, it would print, and then suddenly there will be some droplet dripping down. Because what happens is, even if there's a little bit droplet formation, 2G will just bring it down. So this we needed to fix, right? So what we decided to do was simply to use another filter for these droplets chamber, and then it actually worked. So this is basically the code thing that you see here. Basically, one is time, the other is accelerometer, and the other is position. The yellow regions are near G conditions, and the green region is where actual printing happens. For example, here, the first two parabola are Martian parabola. You see the gravity is about 0.3 to 0.4. The one on the red is the Martian gravity, and green is where the printing happens. So we need to make sure that we print within this condition. We had programmed it because the printhead, it will only start printing only if the accelerometer sees this G. So, and then the orange one is lunar. You see it's like 1/3, 0.2. It's less than 1/3. It's actually 1/4 or 1/5 of the terrestrial gravity. And then in 0G, basically, it hovers around 0. Sometimes you do get negative as well. That means it get pushed. So as you see on the second and third plot, there are some negative G's as well. So in all the cases, we had to make sure that the printing happens within that region. And we also needed to know this because when we analyze the sample, we need to make sure that we only look into the region where actual printing has happened within that 0G time. So as I said, in the fourth flight, we added an additional aerosol chamber to filter the large droplets. And then we had kind of coded, and everything worked fine. There was no droplet formation or anything. And basically, in the center figure here below the interdigitated electrode, you will see that dark patch. So that's like a parking or dump position. So the printhead waits there, and then once it sees the accelerometer goes closer to 0.2G or 0.1G, and then it goes to the parking position. Within few seconds, you get 0G, within a second, basically. So then it starts printing, then it comes back. So some of these were printed in two parabolas. So for example, the interdigitated electrode, one side of it was printed in one parabola, and then another side was printed in another parabola. Same with Wi-Fi antenna, like basically, we printed up to this bottom tip from left, and then we waited, and then on the another parabola, we printed the remaining. So what is interesting is that like within 40 seconds, we printed this, and we were kind of sure that it's not going to work, right? Because basically, these are off-the-shelf nanoparticle inks. So the particles, particles don't spend enough time in the plasma. And 20 seconds is actually way too less. You're printing like several millimeters, per second type printing. So we thought, okay, it's not going to work. These are some of the, again, red and orange is Martian and lunar G, and green is where the printing happened. And we were surprised, actually, all the samples performed well, actually way better than 1G. So we did some SEM analysis, exactly same conditions, except in the only variation is the G. One was printed on ground, another was printed in the flight in 0G. Look at the SEM, you see that because, as I said, the particles spend less amount of time, right? In principle, you should see that the particles are sintered. They don't stay as globular, but because it's a 20 seconds printing, we expect, you don't expect, the sintering to happen within that period. But what is interesting is that, like, you see the particles were kind of forming a well-connected network, between 0G, the one on the left is 0G and 1G. So what we could see is that for the 0G samples, the particles, just a partial sintering is enough. So you don't need to completely sinter. So when you do, like, even at the partial sintering, because of surface tension, instead of being globular, it is, they tend to form this, bean-like structure. So this actually helps in increased conductivity. So what it means is that for the terrestrial application, when you have to go for higher sintering, it works actually better. Even a partial sintering is sufficient to get the necessary conductivity. We actually, we're still working on getting the conductivity number. So we did just some DC resistance measurements for the samples printed on 0G. The DC resistance is 50 times lower than that printed on the ground, which is very interesting. And then we characterized the antenna. One of our collaborators actually did it. We don't have the facility to characterize the antenna, and it actually works, surprisingly works really nice. There was a, it's a Wi-Fi antenna. So, you see the absorption, like it's somewhere around 1.7 or 1.8 gigahertz. And then the film thickness, anywhere between 4 to 5 or 6 micrometers. So overall, the impressions of the flight was that, like, first flight failed due to electrical wiring communication issue. We had to fix that. And then second flight, actually between flight 1 and flight 2, we had actually, after flight 1, we had to reschedule because we knew that there was like a lot of issues. So we had some time between flight 1 and 2. I think we had 2 weeks time. We went back and then we went to Kennedy Space Center, tried to identify issue between flight 2 and 3. Yeah, all we had was just a few hours in the aircraft and then overnight, for coding. So the liquid hardware, when it failed, the flight lands, say, I think around 10:30 or 10:30 or 11. From 11 till 3, you have time. So 3 p.m., they ask us to leave the aircraft because they sanitize, they do all the maintenance stuff, and then we have to report back at 5 a.m. tomorrow and the following day. So we had between 11, 4 hours, 11 to 3, to identify and fix the issue. So it was one of the most stressful time. And then coding and everything happened. And then, between flight 3 and flight 4, we had like 2 days, or maybe, no, we had about 4 days. So it's always better to split, not have everything in one go. So we could identify and fix the problems. So we met the goals for silver printing and copper. We are trying again in June. So we went back to NASA and said that this is how it works. And then they immediately funded the summer flight. I said, okay, you guys can go and finish the copper. So at least we have now credibility established. The printer is robust. The technology works in microgravity. So hopefully we will have demonstrated copper in June. So the whole value that we got out of this flight demo is that because we know that this is the date that you have to do, and every flight was roughly about $50,000. So when we lost 2 flights, NASA said, okay, you have already burned through $100,000. Now, for them, more than the money, the problem is that they wanted basically us to win because they are interested in getting this into ISS. They said, like, if you miss this time, we have a launch happening in 1 year, and then another one in second year, you might miss the window. We won't be able to, go to ISS within this window. So that really put a lot of pressure on us. So we had to customize the fluid delivery and automate the print process. All of this happened. We were able to kind of get some media attention. NASA did a story as well. So then what next is that we need to really establish the relation between the microstructure formation, what happens in 0G, and how it affects the behavior, both electrical and we need to also look into flexible distress. If that have any impact on the crack formation and things like that for flexible electronics. So we have this, and then we are looking into sending this into ISS by June 2023. June might be too difficult, so it's likely towards end of 2023. And then so this has opened up a lot of possibilities. So lunar manufacturing, as I said, NASA is sending, before they send the people, they want to have some facility up and running there. And then use that also to set up proper manufacturing facility in lunar. So lunar manufacturing is probably, relatively easier than ISS because you do have some gravity, right? So handling liquid is to some extent going to be slightly easier. Of course, it's 1/5 of the Earth's gravity. So we have potential to work with the lunar regolith processing. Hopefully in summer, there will be some news coming out of that. And we become an indispensable supply chain for metallization in space and moon, basically. So currently the equipment looks like that. So for ISS launch, one of the challenges is that we really need to compress this. So we'll be working on that. Hopefully the project will get awarded in April. So, and then we will shift our focus completely towards that. Just last 2 minutes, 3 minutes. So just on the background, so the way it all started is that we were trying to, when I was at NASA, Space Foundry doesn't do any biology work. The way it started is that we had, when I was on site as a contractor, we were trying to use synthetic biology for different applications and trying to use plasma for sterilization. Plasma sterilization is well known. You kill, basically plasma kills the microbes. Um, so we had some publication on air decontamination as well. And biosensors was one of our focus. And this is how the system looked like, when we were using this for proof of concept studies. And then, some examples of plasma killing microbes, sensor work, using plasma to functionalize surfaces, basically. And so one of the interesting projects that actually led to this formation of this company is that there was a group working on genetic engineering of microbes. They were basically trying to use microbes to mine the metal. So you pulverize your electronics, put it on a bath containing genetically engineered microbes. Those microbes will go and selectively mine metals, right? So if you just want copper, you can engineer your microbes to mine the copper. So, and then they give me the ink solution, bio ink, because we have already experience in killing microbes, and in semiconductor industry, plasma ashing is a common phenomena where you really oxidize all the hydrocarbons and get it out of the surface. So we thought, okay, we can try to do that, kill the microbe and then do a plasma ashing. But what happens is that copper oxidizes, right? So we said, okay, we can use hydrogen plasma or something like that to reduce. And then we reduced the copper, and that's when we realized that, okay, there is a commercial potential for printed electronics. And actually we started this company. But what we need to do is, like, we need to be revenue generating, can't just focus on space. So we are now actually working with an aerospace and defense company for printing frequency selective surfaces on radomes. Basically, they are really large structures, like the aircraft nose or drones. So you want to have drones with integrated antenna, frequency selective surfaces. Ours is the only technology that's going to enable. So they have tested few things. So we have been selling machines so far. So I think I should just wrap this up in this. So basically, this aerospace company tested some inkjet, aerosol jet techniques, and ours. They need a thickness anywhere between 100 to 300 micrometers. These are metamaterials, frequency selective surface application. Building thickness using inkjet, aerosol jet is going to be complicated, especially if you have a large structure which is not planar, it's three-dimensional. It's going to be very challenging. So they will be mounting our print head onto a really large gantry and go ahead and print these patterns. So that's one vertical we have identified that's going to be revenue generating, so that we can stay in business. Otherwise, you rely too much on government always reimburses money. It's going to be, we can't meet the payroll. So it's going to be very challenging. So we have been selling machines to universities and federal labs. We have desktop system, and we also have robotic arm integration. We are now in discussion with some corporates to see how we can use our proprietary printing process to scale the business. These are robotic arm integration. And these are some of the installations in universities and federal labs. And actually, this is how the product evolved. In 2015, we had, 2012 to 15 or 16, we had one on the left. we had no idea whether that's going to work or not. So we were just trying to use that to demonstrate application, and then we started the company and said, okay, let's try build this machine. And so that's how we productized. And I think, yeah, that's about it. So this is my contact information. Feel free to reach out to me. Sorry, this is a very lengthy presentation, but I, kind of wanted to cover as much as I can.
Sure. I think that, thanks a lot, Ram. I have to thank you for the. I mean, you shared a lot of information about your own flight tests as well. I think that's really helpful. We have our own team here listening to your talk, and we have taken some very baby steps here at ExTeM Group, especially we're looking at some 2.5-second drop tower experiments. And the group, the team that's working on, I mean, I see Aditya, Niket, and Venkat, everybody's here. There's a lot of struggle. I mean, the kind of failures that you talked about, we're actually going through some of those baby steps as well, just for the 2.5-second drop. So I can imagine, the kind of difficulties that you probably face on a parabolic flight. And yeah, so really thank you for sharing some of this, experiments and that you've gone through as well. Yeah, the floor is now open for questions. I'm sure Ram will probably be hanging around a little bit more today, take some questions as well. So yeah, if anybody has a question, just feel free to unmute and ask Ram, please. Yeah. Any questions for Ram?
Yeah. Ram, I have a few questions.
Yeah, sure.
Yeah, very nice presentation. You've given so many details. How nicely you have evolved with your printing technology. So first of all, congratulations for succeeding in your fourth flight. You've been able to print in zero gravity successfully. So one question is, of course, you still have to test copper, right?
Yes.
For antenna applications. Yeah. So when there's a time scale involved from NASA side, why you're going to do this test in June? Why not earlier? Earlier than
Yeah,
June?
no, they have in May. So they run a flight campaign only twice a year.
Okay.
So they usually run in May and November. Okay. But we also need more money. So so you need to say that we have more.
So between silver and copper,
yeah.
What do you think has gone wrong with printing copper compared to silver?
So the mechanism, there is a slight difference. So with silver, basically we are using off-the-shelf ink. Basically, we are taking silver nanoparticle ink and printing, right? So whereas with copper, we will be using our proprietary ink solution, which involves it needs proper residence time. So it's I can't go in detail on the ink. It's basically we use some type of a salt solution. It's a particle-free ink. So the plasma needs to play like a plasma electrochemistry type thing. There is definitely a residence.
One is that is a salt-based one. So the salt has to be burnt out. The salt has to be removed. Yeah. Okay.
Yes.
Whereas this is just a nanoparticle-based ink, silver ink. Which
yes. Yeah. So also, copper needs to be reduced from oxide form.
Yeah. Okay. So basically, the particle sizes are much different. So you can go to very small particle sizes when you use the silver ink. Is it not?
Yes. Yeah. We can. Yeah.
Okay. Or so one more problem is putting silver and copper on Kapton. Maybe the adhesion will be different in both the cases. Did you?
Yes.
Did you try that on the normal lab atmosphere?
Yeah. We looked actually. So the Kapton. So we have to do some pre-treatment. Just need to expose the substrate to plasma prior to printing. Basically, in the code, we just have another line that shows, okay, before the ink comes, plasma treats the substrate. then it's actually works. It's not, we don't have that issue.
So this deposition of the layer, it has to be plasma based. You can't think of any other alternative.
So so that's what, like, so we can use aerosol inkjet. There are companies, one of our competitors that are working on aerosol jet technology. Without plasma, basically you can aerosolize or drop. But the problem is you have to cure. So if you want to build like say 100 micrometer thick trays, conducting trays, so how are you going to do that, right? So you can print, you have to cure, and then again print and then cure. So so when you do that for copper, it oxidizes unless you have you create a vacuum and create a inert atmosphere and have because the atmospheric oxygen is going to react when you're curing.
Okay, that's the reason why in here. Okay. All right. So just one more question about the mining of metals. Can you, in outer space, there's plenty of iridium in meteor.
Yeah.
Can you mine that metal?
So that's actually, like there is, so helium can be extracted. Basically, as of now, the moon doesn't have an atmosphere. So the helium, the gaseous helium is actually buried in the sand. So, for that, you have to basically do an extraction. Generally what they do is basically take the sand, filter it out, and then just heat it. When you heat, all the molecular oxides, then you collect the gas, right? That comes out, anything that gets outgassed from the heating process, you collect the entire gas and then cool it. So, it's going to have all the molecular gases. When you cool, the molecular gases are going to condense much earlier, and helium being, unless you go to very close to 0 Kelvin, helium is not going to liquid, the temperature that you really need to cool down to liquefy helium is way too lower. So you should be able to extract helium fairly easily. But only thing is you need really large structures to, dig this sand and then filter it in particle sizes and then heat it up. And it's not buried too deep like what you see in, coal mine or gold mine or copper mine. It's there in the salt, in the sand. And itself, within 1 meter. Yeah. So
what do you do with that helium gas? I mean, you can liquefy it there, but you can't transport it back to Earth, right?
So there are two things, right? So for us, we can create plasma using the helium. So we can now process the materials on lunar surface without having to worry about taking the cylinders from here, right? And then the second thing is this, everything relies now on SpaceX, right? So the, currently a trip to moon takes about 3 days. But the cost is going to be high. So when Elon Musk brings the cost down, transporting the helium, processed helium there should be feasible. So the main challenge is in establishing the infrastructure there to process. Otherwise, you will have to bring tons and tons of sand.
Yeah.
So that's going to be way too expensive, right? That's so even when we just had a call yesterday with International Space Station. They said, no, after the experiments, we're talking, hey, when will we get our equipment back and how long it's going to stay? They said, no, it's not coming back. They will put that there's a graveyard orbit where all the international players, they all have agreed on certain orbit. where everything will be dumped. So there is a dump orbit, so our equipment will be dumped there. So bringing mass down, is very expensive. Uh,
That's
so
very exciting. Yeah. So Setu, it's very exciting, no, to get helium gas there and pretty. My God, this is amazing.
Yeah, that's
yeah,
true.
see, the interesting thing is, for the when you use nuclear fusion, generally, say you fuse, hydrogen, get helium,
Yeah.
but the isotopes of hydrogen. But helium-3, since it's rare, the helium reactors are not here. But if plenty of helium is available, you can get a reactor. The amount of energy that you get out of helium-3 fusion looks like extremely high. And then the advantage is that you don't have byproduct. Like unlike the uranium and nuclear fission, because the neutron, the radioactive decay problem is there. Whereas in helium-3 fusion, there's no radioactive decay. So this is the cleanest form of energy that you can get. Obviously, apart from solar.
Oh, pretty exciting. Okay, thank you.
Professor Mohan, you have a question? Then we'll move on to Hemang Jayant. Yeah, Professor Mohan.
Yeah. So thank you, Rom. It was a fantastic lecture. We already discussed some of those things. The talk talks about basically two things. One is the development of the system, technology. The other one is business. We have already discussed about the business part, and these details in the talk really put lots of questions. This involves basically the instrument development and the materials development and the process parameters which affect the structure. Many more questions, but I don't think we can answer all those questions. We can ask all those questions. Very interesting, but there are solutions for these things. But as Professor Rao put it, are you very specific about the technique? It's a jet technique, jet plasma. It has got its own inherent problems. Is there any other thing? Now that you are stuck to this technique, how you are going to solve the problems of the process parameter, structure, electrical properties, correlations? That is the most important thing. I think we'll be able to sort out most of these things. Yes, as you are looking at the business, there will be many more groups who can solve these problems. Wish you all the best. We can continue the discussion because this is not the time to discuss all the questions. Thank you very much.
Thank
you,
Professor.
Sachin.
Yeah, thanks, Professor Mohan. Hemang Jayant, you have a question? Yeah.
Yeah, hello Ram sir. It was a congratulations for printing in zero gravity first of all, and it was a nice presentation with the tangible results. I have few questions regarding the technology, also the future aspect of plasma jet printing. So I'll start with the basic one. You said that plasma doesn't need to cure the printed part. Is it correct, or do you still have to cure that printed structure?
No, you don't have to cure. You can treat with the plasma. You can have code in such a way that once the print, once the ink inlet is, you stop the ink flow and then you treat the plasma continuously. So it's not
plasma.
Yeah.
Okay.
Yeah.
Actually, we are also working on droplet on demand based metal printing for electronic structure, and I have completed my PhD from ISC.
Oh, okay.
We are mostly focused in the electronic printing only in 3 dimension, 2 dimension and 3 dimension also. So is this plasma jet printing is looking into 3 dimension of electronic printing or?
Yes, we are doing. Yes, some of the aerospace applications that we are talking.
Is there a scope in zero gravity printing for the droplet on demand based additive manufacturing process?
So, so one of the things, so it for different it depends on what application and what material you're doing. So, we are not going to be able to do whole range of materials. So, every technology will have its own inherent advantages and inherent limitations, right?
Okay.
So, so what material are you gonna, try?
Okay.
Do you have any particular materials in mind, or you are working on more on?
We are working on the low melting point material tin and silver, tin-based silver alloy, and we are more focusing next for the aluminum-based alloys.
Yeah. So that will, I think, silver is actually filled with, even we were not interested to do silver, but NASA wanted us to do that for just like a, risk mitigation, at least, whether we'll get to know whether the technology works or not, then you can always say that, okay, this is what you are doing. So, alloying is something that's going to be very important.
Yes.
My suggestion will be just, silver, silver has advantages, but so many, it's like companies that are working on silver. But alloying is something that, is going to be challenging.
Okay. And tin-based alloy is still a challenging process, is it?
Yes.
And other than this electronic printing, is NASA is open for the additive manufacturing of the mechanical structures also, or they are not looking into that?
No, yes, they are, because there's a huge focus on additive manufacturing. Because for these, they're basically building a habitat in lunar, using additive manufacturing.
It will be nice if we can connect after this discussion over email or something. I'll ask my professor also to connect with you.
Yeah, sure. So with whom were you working there?
Dr. Manish Arora. It's
Okay.
a Center for Product Design and Manufacturing department in ISC, Indian Institute of Science.
Oh, okay. I think I probably came there maybe 3 years ago.
Yes, I've seen your presentation.
Okay. Yeah, okay. Yeah, I was talking to, Professor Navkant Bhatt, and then he suggested, I was trying to see if we can install a system there in ISC. Of course, back then our product was not fully mature.
Yes.
So he asked me to give a, talk in your department.
Okay.
Yeah.
So it's good if we can get connect through for this to featurize the droplet on demand or plasma jet printing and for the additive manufacturing in zero gravity.
Yeah, sure. Yeah.
Thank you, sir.
Thanks. Yeah.
Okay, other questions for Ram? Any other questions?
Ram, Sachin, I'm coming back again.
Sure, go ahead.
So, Ram, what is that absence of magnetic field there in that slide?
Yeah. So, we have the Earth's magnetic field, right? So the moon doesn't have the magnetic field. So the solar flare, right? So our Earth magnetic field protects the Earth, from all the solar flare events.
That's not the case on moon.
In moon, yeah. That's why you get all these helium-3. See, the helium-3 is basically byproduct of nuclear, fusion, basically. Yes. So you do get a helium-3 here in Earth, when you do, the amount of helium that you will get is very tiny.
So how far below the moon surface you said it's buried?
It's within 1 meter. It's, you don't have to go deeper.
Okay. That's interesting. So of course it's the 1 ton of helium costs about $3 billion US. How much it costs to transport 1 ton of helium to Earth?
Yeah, so that's the one thing. But you can bring that basically one space shuttle completely filled with helium-3 can power, just one shuttle can power, from what I understand, can power an entire state for one complete year.
MSRE, I know I think the numbers that excuse me, Ram mentioned was $3,000 per kilogram is what Elon Musk is targeting. With that, if you multiply by 1,000, it's $3 million transportation costs. Yeah.
No, so, but that is currently, right?
Yeah.
He is working towards bringing it to 100.
$100. Yeah, correct. The number was 100. Yeah.
Yeah.
So 100 into, I mean, it's 10 power 5, basically. Yeah. One tenth of a million, basically. Yeah.
Like, so you see the whole, see all these companies, right? See, the Varda space was funded by this guy, Vinod Khosla. So I talked to one of the guys that just 2-3 days back is one Desi guy, Mukund Pandian. So basically they're building a space station and they are trying to solve. See, the problem is when you are entering the Earth, right? Everything gets crushed. All the, especially on the human organ manufacturing, things like that. So they are solving that problem. And this Axiom space now, they are building, like what you see is a graphic of their, so they are building a completely remote, unmanned space station where they want to use for manufacturing semiconductor chips and things like that. So they want to have a fully, because obviously, for a lot of things, you're going to have toxic materials, chemicals, and it's going to be extremely difficult to have people working in the same spacecraft if you want to really deal with a lot of materials. So they're working on building a completely unmanned space station. And then this guy, Orbital Rift, the Jeff Bezos guy, so, he's building this research park, business park there. So all of this is dependent on Elon Musk. Right now, we also have this rocket lab that's coming up from New Zealand. But it's primarily, all these people are investing in the belief that Elon Musk will bring the price down.
Let's say, Ram, so let's say billions of dollars are spent to establish some labs on moon. I mean, you can harness helium, you can produce low temperatures, you can even sort of set up these exciting experiments that require extremely low temperatures. All that is fine. But then what happens if a solar flame hits the moon? Because there's no protection there.
No.
So how would one protect himself or his land?
So they call, they have some, it's, there is something called some type of tunnel type natural thing is there where they are looking at now. No.
Yeah, now I can hear you. Yeah.
Okay. So they have identified certain locations which are actually very safe. Okay. It provide like a natural shelter type of places have already been identified, where they say that these locations could be ideal.
Right.
Okay, I think maybe one more question, Ram. I think Naga Praveen, I think you had a question. Praveen Babu.
Yeah, yes, sir.
Yeah, go ahead. Yeah.
Sir, I was working on insect flight at low Reynolds number. So if I want to test that insect flight using thermo vacuum chamber or zero gravity, is it feasible to conduct experiments there?
Sorry, what is that on?
Insect flight, sir. It's an unmanned UAV. It's a bio-inspired UAV.
Okay.
Insect flights, huh?
Yeah, yes. At low Reynolds number environments.
Okay. So,
is it feasible to conduct experiments at thermo vacuum chamber or this zero gravity conditions?
So you will have your so they allow payload. So I see basically see you can reduce your volume. I'll show you my can you see this new screen or
yeah, I can see it. Yeah.
Yes.
So this is our system. See DC you can reduce, it's too noisy. Reduce the volume. So if you see here, so there are different groups there. You can see on the next the multiple groups. The guys that you see at the back side,
Yes, sir.
Next to us, right, left, you see this one.
Yes, sir.
This is a company, one of the companies that Jeff Bezos has funded, Redwire. So they are doing actually welding.
Okay.
So, you know, so you, and there was one group that was working on a plant from Kennedy Space Center. See what they were working on. I don't know what they were doing there. You know, watering the plant in ISS is challenging because of surface tension. The water just goes to the you know, top of the plant rather than going down to the root. So the, you know, so you can have multiple of these. See, there are different groups working on. So you, as long as this is the workspace, you know, this is the aircraft. So you get about 10 feet by 10 feet. This is our gas cylinder. So, you know, you get a fairly good area. As long as you can bring your system there, you know, we needed to put all these, you know, our printer need not be in this huge size, but we had to get a, see, bottom plate. Do you see? There's a big bottom plate that's like really heavy. So that was bolted onto the floor. We had to do everything by ourselves. Obviously, the only thing that the guys that they will do that, they will bring a forklift and they will have the appropriate screws. That's it. So you don't get any other support. So you need to be fully prepared. And then, you know, this was, you know, we had to do a calculation to show that this payload will withstand up to 9G.
Okay.
So those things I can all share.
Sir, can we simulate similarly like in Martian density?
Yeah. So this is the space that you will have. So, you know.
Yeah, so I think as Ram mentioned, Praveen Babu, you know, it has both, you can get both lunar gravity and Martian gravity time as well.
Yes,
I'm not sure what the time duration is for lunar G and Martian G, that Ram can probably say, but yeah, there is all the three. I mean, you can get different Gs as well that you can simulate in the parabolic flight. Yeah.
Okay, sir. Okay.
Yeah.
Thank you, Professor.
Okay.
Yeah.
Okay, any other questions for Ram? I think we have sort of gone 15 minutes past the hour there. So anyway, so thank you again for Ram for you know, coming online here pretty early in the morning there, and then sharing with us your valuable experiences that in parabolic flights. I really appreciate it. Thanks again, and yeah, I look forward to continuing the connection with you with our ExTeM Center as well. Thank you. Yeah.
Yeah. Thank you very much, Professor. Yeah.
Okay. Thanks. Bye
everyone.
bye.
Yeah.
Bye.
Thanks.
Bye.
Yeah.
Thanks, Ram.
Bye.
Very nice. All the best.
Thank you,
Thank
sir.
you, sir. Yeah, Professor Rao, let's discuss. Let's see if we can bring helium. You know, like remember the Chinnakallu Bettalavam, same thing we have to do, you know.
Exactly. Ram, my colleague, you know, Professor Setu, we work together. He's in the LT lab where, you know, this is one
lot of helium.
Lot of helium. I think this is the Chinnakallu Pedalavam thing. We should do it.
Yeah, let us become rich. You know, there's too much of academia. You know, you see all these people here, software people from everywhere. We are the only people with all intellectual and have no money.
No money. Sir, Mohan, what he says is the Chinnakallu Pedalabam is small stone and big profit. I think that's we discussed about that Chinnakallu thing. I think let's make it happen, man. Right?
Yeah.
Definitely.
Setu?
Yeah, very interesting, Dr. Ram, and I'm happy that you are from PhD Tech and then you've done PhD.
He's the guy. This guy is also from Coimbatore.
I am from Coimbatore, so I'm just happy and nice to see.
Oh, okay.
Good.
Oh, that's
By
great.
the way, Professor Setu, Ram has other plans in Coimbatore as well, which doesn't come under this umbrella, but he is cooking some of the things cooking up in Coimbatore as well.
Oh,
Yes, sir. I'm planning to come in March or April, I think.
Come over. We'll keep all the Chinnakallu ready by then.
We tried hard to bring him to Research Park, but Coimbatore was his hometown, I guess. So
Yeah.
Cool.
Yeah.
We'll discuss
nice
about
to
it.
see Professor Mohan after a long time. Professor Mohan, how are you?
Fine. How are you, Professor Setupati? Good. It's an opportunity. Thanks to you. Thanks to Ram.
No.
I mean, if I had not met Ram, probably I would not have come here. I met Ram 2 months back, and then we had a lot of discussions, multiple meetings. Now he, in fact, cleared most of the questions, and then most of the doubts are cleared. But there is a lot more. As I said, technology on one side, business on one side.
That's
So
true.
I started with business. Now it is an opportunity to talk about technology with him.
Now the big thing is to bring helium to
Helium
the
from there, yes. Now I
Yeah,
think
from
Yeah.
moon to Earth, right? That's the
especially
thing.
helium-3, we don't have it at all.
don't
Helium-4
have it
at
at
least
all.
we're managing, but helium-3 is very, very expensive.
And for all these critical quantum computing experiments and all that, helium-3 is required. You need
yeah.
millikelvin temperatures, and it's going to be tough.
Sir,
But
let
Professor Ram,
us
I
start
think,
another startup. I'm open for that.
Let's
You
do
know.
it. Yeah, Ram, come.
Nah,
We'll discuss March. Huh? You're coming in March?
yeah.
Yeah, sure. Yeah.
I think, Professor Rao, this material processing is going to be very important for various metals.
Sir, one of
That's
the things
going to be
is,
a very interesting thing.
see, of course, the next generation material element is going to be iridium. And there's a lot of iridium in the outer space. So to harness that is very important, and that's something we should seriously think about, Ram.
Yeah.
Iridium is lightweight, high melting point, and also high strength. You don't get iridium.
Okay.
All meteorites have a lot of iridium.
Oh, okay.
Source is meteorites. There, up there.
Oh, okay.
So we'll have a startup on iridium and also helium gas.